So what was work in the non-angular realm? Remember, it's just a force applied through a distance. So if we're talking about rotational work, then it's still the same thing, force through a distance, but it's our force is now a torque, and so it's only this tangential force. So it's this force, and then this force, and then this force, right? And so these are bike pedals here, and this is a chain on a gear, and this is what turns the wheels. And so when you push down on pedals, or push forward, these are lever arms that are providing a torque on the gear here, on the particles that make up this body, which are connected to the chain, which are connected to this body over here, which are connected to that wheel, and that's how you go forward. So you're applying a torque, but you're not just applying a momentary torque that exists for just a blip and then goes away. You're providing a constant torque, and so that would be known as work. And so work for angular things has its own definition. We're probably not surprised. We're just basically filling out the rest of these things that we already defined in the non-rotational realm, and now we have new definitions for things that are rotating, because we have new quantities. So we have, instead of just regular position, like x position, we have angular position, theta, remember? And so if work is a force through a distance, and our force is now torque, and our distance is now angular distance, then it may come as no surprise that work for rotational stuff is going to be the torque times the angular distance covered. So torque through a distance, which is equal to torque delta theta. Right? And for changing torque, or you could say in general, because you can use the integral even if there isn't changing torque, and it just reduces to this basic guy here. But the general definition would involve an integral, right, from theta 1 to theta 2 of the torque d theta. So I'll box this one in because this is the more general one, whereas the one above only applies to constant torque. And it can also be shown in the same way that we did for non-rotational work and kinetic energy, that the total change in work is equal to the change in rotational kinetic energy of a rigid rotating body. So in other words, the work energy theorem can be expressed rotationally, to nobody's surprise at all. And that goes like this. Work total is equal to, from omega 1 to omega 2, I omega z, right, in the z direction, the omega z. I guess I haven't been writing these, so I won't add them now. And this will make a little bit more sense when you get this next sign here, because this is what you probably remember as rotational kinetic energy, right? 1/2 I omega squared. But that was omega 2 squared minus 1/2 I omega 1 squared. Right, so the work total is equal to the change in rotational kinetic energy. So work energy theorem for rotating things, right? It's not too different once you kind of remember to mentally substitute and why we need to. And then likewise, the power associated with work done by a torque acting on a rotating body is just a time derivative of this work. It's time derivative of work. So d work dt is equal to tau, the torque, d theta dt. There it is. The time derivative of work is known as power. This is the same term power. And the time derivative of the angular position is angular velocity. Right? So we can just write torque omega. And this is power in the rotational world. And so we kind of went through how to use all these and what the concepts behind what work is and what power is. So there's not a whole lot to expand on. We're just giving the rotational analog to these things. And so I'm not going to do examples that show how to apply this as much, because I think that it's pretty intuitive how to translate just from the linear stuff we've talked extensively about to this rotational stuff.